Okay, so I think that last time we derived the Boltzmann equation in the case of non-interacting particles, and we said, okay, so first of all, what is the distribution function f of r, p, and t? Is a quantity that basically allows us to count the number of particles with a certain momentum and certain position. Okay, so the quantity f of r, p, and t times dr dp determines the number of particles that are in a small volume of centered around r and p in the mu space. Okay. And we said that without interaction between particles, non-interaction, so non-interacting particles, what happens is that the total derivative of f with respect to time is equal to 0, which was in turn the derivative of f, the partial derivative of f with respect to t, plus then we had the gradient with respect to the coordinates times p divided by m, the gradient of f, of course, the gradient pf scalar f equal to 0. So this was the case of the Boltzmann equation in the case in which there are no particles, there are no interaction between particles. Now we have said that particles can interact, okay, so interaction. And this interaction is characterized by two features. First of all, they interact when they are in the same position. In space. Okay. And therefore, to this purpose, what we consider is a scattering, basically, of particles, initial particles, for instance, with momentum p and p2, that provides the same two particles, but with momentum p1 prime plus p2 prime. Okay, so this is a two-body interaction, two-body scattering with initial momenta and final momenta. Okay. Now, of course, when counting the number, when considering this interaction, there is a thing that one should introduce in the calculation, which is the dn number of pairs that are in the initial state. So the number of pairs of particles with momenta between p and p plus dp and p2 plus dp2. And this is equal to, say, dr dp dp2. And here we have a two-body correlation function, which is a function of r, p, p2, and in general also of time. Okay, so this is a two-body correlation function. Well, actually, it's a two-body distribution function, but basically, the correlation will actually be the difference between this function here and the product of the two single particle function. This will be the correlation. So it's better to call it two-body distribution function, okay? Distribution. Although they are basically the same. Okay? So what does this? It counts the number of particles at position r with momenta between p and p plus dp and p2 plus dp2. Okay, so basically that allows us to count the number of particles having an interaction around the point r with the specified momenta. Now, The rate of collision is basically provided. So what happens in a scattering process is provided by the Fermi golden rule. That you might remember from the course of subatomic physics. I don't know if you have heard about this. Maybe yes, maybe not. Yes. Okay, you know that. Okay. So that tells us that basically the rate of collisions or interaction is something like that. It's a matrix element TIF squared. So this is a matrix element that tells us basically the probability to go from a final state, from an initial state that I call I, to a final state F. In this case, the initial states and the final states are just determined by the momenta. So the probability of that once P and P2 are fixed, which is the probability to obtain from the scattering particles that are produced with momenta P1 prime and P2 prime. And so the rate of collision will be basically proportional to a matrix element in which we hide all the physics all the microphysics, basically. So we are not going to compute TIF in any case, at least in this course. Then there is a delta 3 of conservation of momentum, which is P plus P2 minus P1 prime minus P2 prime, which is the conservation of momentum. Then there is time, the conservation of energy, which is E, where E refers to P, plus E2 minus E1 prime, and I guess I have to go here, E minus E2 plus E2 minus E1 prime minus E2 prime, which is the conservation of energy, okay? And of course, from the Fermi golden rule, we have also to multiply this by the phase space, okay? So let me write it down in a better way, okay? Otherwise, it's too... So let's say rate of collision is proportional to TIF squared. Then there is a delta of momentum conservation. Then there is a delta of energy conservation. And then there is the phase space. So dP1 prime, dP2 prime. This is the phase space of the final state. Okay, so this is the structure of the Fermi golden rule. You have a matrix element, you have a delta of conservation of energy and momentum, and then you have the final phase space. So therefore, when computing R, last time we said that once we have the interactions, we have to write that the right-hand side of the Boltzmann equation is the derivative of F collisional, which is the collisional term. And we said that this is R bar minus R, where R bar it's basically... Ah, non dimenticato. Grazie, scusate. Okay, so derivative of F collisional is R bar minus R, where R bar and R basically counts the number of, tells you how the volume around R and around P is enriched by particles or depleted by the particles due to the interactions, okay? So basically, R prime was the contribution of particles coming in the element volume centered around R and P, whereas R is counts the number of particles that in the initial state were in R and P, and then in the final state are no more in that volume of the mu space. And so we can write R as follows. So R will be an integral of dp2, so we are integrating over the momenta p2, p1 and p2, p1 prime and p2 prime. Then we have the matrix element squared. Then we have the conservation of energy and momentum. And here we have to add now the two-body distribution function, which was the following: R, then we add P, P2, and T. Okay, so the term R that was counting the number of, the number of particles exiting the initial, so the volume element centered around R and P, is done by integrating over these three momenta, the matrix element, the conservation of energy, and this is the probability. Well, this counts basically the number of particles, the probability that particles, the two particles are in the position R with momenta P and P2 as a function of time. Okay. One observation that we need to do is the following, is that the TIF squared will be something like a matrix element in which in the final state we have P1 prime, P2 prime. Here we have a transition matrix that we are not going to compute, that contains the microphysics. Then we have P and P2 squared. Now this is equal in the situation of time reversal. If time reversal is fulfilled, this is equal to the same matrix element that we obtain by inverting the initial state and the final state, okay, under time reversal. Actually, this can be shown in scattering theory for certain Hamiltonian, and typically the Hamiltonian that we use are, they have time reversal, but for the weak interaction in which there is a small deviation from CP and therefore also time reversal. But let's say that in the easiest cases, we have time reversal. So therefore, by inverting the initial and the final state, the matrix element is the same. Okay. Time reversal means that you switch the sign of time, so you go back on time, okay? R bar, I remind you that R was counting the number of particles, the number of scattering that were depleting my volume, whereas R bar counts the number of particles entering in my volume centered around R and P. And so this R bar similarly is equal to the integral over dp2 dp1 prime dp2 prime. Here I have the matrix element TFI, because now the scattering process is P1, P2 prime going to P and P2, okay, for what I said before. Now we are producing a particle with momentum P, whereas before we were starting with a particle with momentum P, which is not integrated, whereas all the other momenta we are integrating on for all the other momenta, okay? Then there is the conservation of energy and momentum that has the same formula as before. Then we have the two-body distribution function, which is again a function of R because the interaction is occurring at the position R. And what are the momenta here? They are P1 prime, P2 prime, and then time. Okay? So the expression is the same as before, but for the fact that we are switching from P2 as initial state to P1 prime, P2 prime as initial state. Therefore, the difference between R and R bar and minus R, which was exactly the modification of the Boltzmann equation in presence of interaction, can be written as in the following way. This is an integral of dp2 dp1 prime dp2 prime. Then we have TIF squared, this because TIF squared is equal to TFI squared, as I said before, for time reversal. Then we have the conservation of momentum, the conservation of energy that I'm not going to write, which is the same. And then here we have to be careful. There is the F, sorry, here is not a vector, of R P1 prime, P2 prime T minus F of R P, P2 and T. So this is the final expression. This is R minus R bar minus R, and this is what is called the collisional integral. That one has to compute in order to take into account interactions within the Boltzmann equation theory. Now let me change page. Now, of course, let me write again the Boltzmann equation, derivative of f with respect to t plus gradient r f scalar p divided by m plus gradient p of f scalar f equal to r bar minus r, which was the derivative of f collisional. Now, of course, R bar minus R contain a function which is the two-body distribution function. No, they depends on f of R P1 prime, so P1 prime P2 f of R P2 T and f of R P1 prime P2 prime T, which is unknown. Okay, so on the left hand side we have the one body distribution function, whereas on the right hand side we have a two body distribution function. Actually, one can write a sort of hierarchy of equations that somehow link the one body, the two body, the three body distribution functions. We are not going to do that, but what we are going to do instead is to introduce the main assumption of the Boltzmann equation, introduce the so-called molecular chaos assumption. what is the this assumption? What is the role of this assumption? How do we express it? Well, basically, this assumption tells us that f of r p2 t, and similarly for f of r p1 prime p2 prime t, can be written just as the product of the one-body correlation functions. Okay, so this is the molecular chaos assumption that basically tells us that the two-body is just the product of the one body. So there are no two-body correlations, basically. Okay. So the momenta are uncorrelated. So the probability of having in a same position R particles with momentum P and P2 is just the product of the probability of having particles in position R with momentum P times the probability of having particles in position R with momentum P2. Okay, so basically momenta are uncorrelated. Okay, now this is the main assumption of the Boltzmann equation on which basically all the criticism also for the against the Boltzmann equation derived. You might have read something about that, or you might want to read something about that. But the Boltzmann equation, as we will see, is an attempt to derive the law of increase of entropy in terms of microphysics. So it's a sort of process in which you reduce the second principle of thermodynamics to the molecular dynamics. Okay, so it's very interesting because this is very important to have a microphysical explanation of the second principle of thermodynamics. And also, as we will comment later, on the fact that on a macroscopic level, we do not see time reversal. Okay, but I will come back to this later. But the main hypothesis and the main, basically the resulting, the result of the Boltzmann equation is basically due to this hypothesis of molecular chaos, which is not very bad as an assumption, because we have so many particles, we have a complicated macroscopic system, so it's particularly, so it's reasonable, let's say, to assume that at least if we look at the dynamics of the system on time scales that are not too small, basically the momenta of particles are uncorrelated. Okay. At this level, actually, this assumption is necessary in order to close the equation, because otherwise we cannot do anything with the Boltzmann equation. Whereas by using this assumption, now we can write the Boltzmann equation in its final form, that is the following: the total derivative of f, which was the following. Now this is equal to the collisional integral, which is dp2 dp1 prime dp2 prime TIF squared, conservation of energy, delta 3 and delta energy, momentum conservation. And sì, dimmi. Pronto? Non sento più.
Prof, mi sente?
Sì, sento adesso.
Ah sì, scusi, volevo chiederle, potrebbe scrivere più grande perché ho difficoltà per i pedici e le potenze.
Okay. Sì, va bene,
Sì.
ok.
Scusi il disturbo, la
No,
ringrazio.
non ci mancherebbe, io scrivo sempre piccolo, questo è il mio problema. And then, okay, so we have the delta of conservation of energy and moment. And then we have here, now we can use the molecular chaos hypothesis. And therefore, we will have a f of r, p1 prime P2 prime T times the F of R. Sorry, sorry. Let's go down. So I have the F of R P1 prime T times the F of R P2 prime T, because we are using the hypothesis of molecular chaos, of course, minus what we had before. So what is F of R P and T, and F of R P2 and T. Okay. Now you see that, okay, so let us comment on that. So first of all, these equations, the solution of this equation is a function that depends on R, P, and T. So you have in total 7 independent variables. And indeed, you are deriving on the left-hand side with respect to T, to R, and P. Whereas on the right-hand side, you have the integral over dp2, dp1 prime, dp2 prime. You have a conservation of energy and momentum, which allows us to remove some of those integral. And in the integrand, you have also the same function f, which is the unknown. Okay, so this is an example of a very complicated equation, which is an integral differential and integral equation at the same time, no? Because f appears as in the left-hand side with derivatives, and then it appears in the right-hand side with the integral. Okay, so it's a very complicated integral and differential equations that needs to be solved with numerical, so by using heavy numerics. But although it is very complicated to solve this equation, actually it is done in the sense that in present research, this kind of equations, similar to the Boltzmann equation, are used in many contexts of research. As I said, for instance, in the context of astrophysics, for instance, for describing the flux of neutrinos in a supernova, for instance, or also in cosmology. It is used in cosmology, for instance, studying the evolution of the chemical composition of the early universe, and also in that case, one uses the Boltzmann equation. The Boltzmann equation is basically something that one can use in order to describe systems which are out of equilibrium. Okay, so let me write this down because this is important. So the previous equation, so the Boltzmann equation.
Prof, il foglio, scusi.
Certo, grazie. Out of thermodynamical equilibrium. It's very complicated. Everything that is non-equilibrium is complicated. And here we have indeed a dependence on R, on P, and on T. And it allows, for instance, as I said before, to study the distribution and the flux then of neutrinos in a supernova. Why one has to use the Boltzmann equation? Because neutrinos are not in chemical equilibrium, well, in thermodynamical equilibrium with the baryonic component, because they are weakly interacting, and then basically they're not in thermodynamical equilibrium. Okay, they can interact with the baryons, but they are not in thermodynamical equilibrium with them. Actually, they could have a different temperature in principle, or in any case, they are not described by an equilibrium distribution function. Now, just one comment. When we have in the integral dp2 dp1 prime dp2 prime tif squared, and then we have the delta 3 of p plus p2 minus p1 prime minus p2 prime, and the delta of e plus e2 minus e1 prime minus e2 prime. Then here we have the product of the function that I'm not writing here, otherwise we spend hours in writing this. So in principle, now we have three integrals that needs to be done, but actually one of them is removed, if you want, by the delta 3 of the conservation of momentum, and the other, and there is another single integral that can be removed by conservation of energy. Okay, so actually, one they can use the delta function and reduce the integral to a simple to an integral having let's say here you have in total 9 variables on which you are integrating, and you have 4 constraints determined by the delta, and therefore at the end you have a 5-dimensional integral. Okay, 5-dimensional integral. That could be, for instance, the integral over dp2 and a certain solid angle, where this is the solid angle around or determined by the direction of p2 prime, for instance. And here one can show that when doing this integral, what happens is that there is the appearance of the differential cross-section. Which is a typical microphysics component. Okay, now we are not going to show this calculation, it's a little bit boring, but in principle you know that from the Fermi golden rule, once you do the integral over phase space using the delta, then at the end you will get a rate of collision or a cross-section, differential cross-section. Okay, so let's move on. And let's see what happens. So let me write again the Boltzmann equation. Plus gradient Rf scalar P divided by M plus gradient P F scalar F, and then we have the integral over dp2 dp1 prime dp2 prime tif squared, the delta 3 and the delta. So let me write this in a this term now in a simple way. Suppose that we call F the symbol F of R, P, and T, F2 the F of R, P2, and T, F1 prime F of R, P1 prime T, and F of F2 prime F of R, P2 prime, and T, just to make easier, the notation a little bit easier and faster to write. So then here we will have the integral, we will have F1 prime, F2 prime minus F times F2. Okay? Now, let's try to find a solution at equilibrium. Okay, now, but let's do it under two assumptions. Assume that F is equal to 0, so no external field. To assume, and this is justified also by the fact that we are not assuming an external field, we are assuming the external field is 0, assume that F does not depend on R. So it's uniform in space. It's not uniform in momentum, but it's uniform in space. Under this assumption, of course, now what happens is that the Boltzmann distribution is basically the following. dF dt is equal to dF dt collisional. And let's try to find the situation, the stationary situation of this equation, or the equilibrium. Indeed, the stationary solution of this equation, under the hypothesis that we don't have dependence on R, and under the hypothesis that the external field is 0, the stationary solution of this equation, let's call it F0, is basically what we call the equilibrium distribution function.
Professore, scusi?
Sì?
Risulta ancora un po' piccola la scrittura, sì.
Ah, scusate, è vero. No, fate bene a dirmelo, io scrivo sempre largo, è piccolo.
Grazie.
Okay, so the stationary solution of this equation, let's call it F0, is the equilibrium distribution function. Why equilibrium? Because equilibrium for us is a situation in which we don't have any time dependence, no? The thermodynamical equilibrium is a state in which the system basically doesn't change its status, no? It's in a stationary state. Therefore, to obtain F0, which means the distribution at the equilibrium, so in which there is no time dependence anymore. Indeed, F0 in general depends on R and T, but in this case is just a function for our assumption of P. Okay, so no time dependence. And how to obtain this solution? Well, we just need to impose that 0 is equal to dF dt. And for what we have written here, imposing that f does not depend on t means that I have to impose that dF dt collisional is equal to 0. But by looking at the expression that we are here for the collisional integral, this means that we need to impose to 0 the only part of the integral that can be 0, which is this difference between distribution function. And so what we need to impose is that F0 1 prime F0 2 prime minus F0 F0 2 is equal to 0. Okay, where I'm inserting here, instead of F1 prime, F2 prime, the F0, okay, which is the stationary solution. And also instead of F and F2, we introduce F0 and F02. Therefore, F02 prime, F01 prime is equal to F0, F02. Those are functions. Let me change, well, no, let me write it here. F02 prime is a function of P2 prime, and F01 prime is a function of P1 prime. And see, this is equal to F0, which is a function of P, and F02, which is a function of P2. Okay, so let me change page. And take the log of the previous equation, and we get the log of F what I wrote before. Okay, okay, sorry. What I wrote before is that F02 prime, F01 prime is equal to F0 and F02, which written explicitly is, sorry, before I didn't write correctly, this is the F0 of P2 prime, because with the symbol F0 prime, 02 prime, we say basically F0 of P2 prime and F0 P1 prime, sorry for that. Then we have the F0 of P and the F0 of P2. Okay, so this is the equation. Okay. When we write explicitly the dependence on the momentum, you do not need to put a prime on the distribution function. The notation, sorry, is a little bit heavy. Now take the log of this, take the log, and so we have the logarithm of F0 P2 prime plus the logarithm of F0 P1 prime is equal to the logarithm of F0 of P plus the logarithm of F0 P2. Okay. Now you see that this is something, so it's a scalar equation in which we say that after something after the collision is equal to something before the collision. So it's one equation, one scalar equation, which somehow is telling us that we have a conserved quantities. One scalar equation telling us that we have something that is conserved, expressing a conservation law. Okay. Now, what is the quantity, the scalar quantity that is conserved before and after the collision is the energy. Okay. So this is just the energy conservation. So an equation which will be, since we have all particles with the same mass, the equation will be actually P1 prime squared plus P2 prime squared is equal to P squared plus P2 squared. Okay. So actually, by comparing this equation here and this equation here, I can assume that the logarithm of F0P is actually proportional to P squared. In such a way that the equation that we had before, which is a scalar equation expressing a conservation of a quantity, is just the energy conservation. From which we derive that, well, the logarithm of, well, we take the, so the logarithm of F0P is equal to a certain constant AP squared, with a minus, and let's define A as a positive number. Well, why we do that? Because as we will see in a moment, we need something that can be integrated over momentum, no? Okay, remember that F0 P is a momentum distribution. And therefore, if I do the integral of F0P in dP, this must be finite, okay? So therefore, the constant that I need to put there must be a negative constant, okay? Now take the exponential of this function, and the F0 of P will be proportional to e to the minus a p squared times a constant of normalization, where C is a normalization constant. Okay. So the stationary solution of the Boltzmann equation, at least in the case in which we do not have an external field, we have an uniform system, has the form which is basically a Gaussian. Okay. Now, what we need to do now is to derive by using the constraints that we have or something that we know from thermodynamics, we need to determine A and C. We need to determine, so how to determine A and C. Well, remember that f of, and so therefore also f0 of r p, well, okay, remember this one first. dn is f of r p t dr dp in general. So therefore, if I am integrating over momentum and over position, I get the total number of particles n is the integral over dr dp of f of r p and t. Okay, which means also that for uniform system, actually f, r and p and t is a function just of p and t. There is no dependence, no, on time. For uniform system and stationary, df is actually a function f0, which is a function just of p. Therefore, n is equal to volume integral over dp of f0 of p, which means also that then the density of particles is equal to dp f0p. And this is the density of particles for a uniform system, okay? So basically, due to the fact that F0 does not depend on R and does not depend on T, well, the dependence on T is not important in this case, but if we have a uniform system, the integral over dP of F0P must be equal to the density of particles. Therefore, we have a constraint. Now, this is the integral from 0 to plus infinity of 4 pi dP p squared, and we have c e to the minus p squared a, from which we can derive c as a function of a. Okay, so you can do this integral. It's basically one can do by parts this integral, and you get that. Let me just write the results. That 4 pi c then I have a square root of pi divided by 4a to the power of 3/2 is equal to n, so to the density of particles, which means that C is n times a divided by pi to the power of 3/2. Therefore, we can already write a better expression for F0, which is F0 of P is equal to a divided by pi to the power of 3/2. Then we have a density of particles, n, for a uniform system, and minus a p squared. Okay? So now next goal will be to determine the factor that we have there, which is a. So determine a. I can anticipate the result. What we are going to obtain is the Maxwell-Boltzmann distribution for the momentum of particles. Okay, but so to do that, to show that, we need first to do some kinetic theory. Well, actually, what I'm going to remind you is a result from kinetic theory that you probably have done in the course of general physics. Which was the following. You have a box here with some particles inside, which is exactly the situation that we have here. And then you have a particle, so you want to express which is the pressure of the gas. The pressure of the gas, and basically how the pressure of the gas in terms of microphysical quantities. Now, the calculation, I'm pretty sure, was done in general physics course, and basically is the following. The idea is the following. So suppose that you have the one wall of the box containing the particles, and you have particles interacting with this ball, well, actually going and colliding with the wall and then going back here. Okay? Is a total reflection of the particle for a scattering within a, let's say, light particle and a wall which has infinite mass. So basically here, the momentum, the change of the momentum of the gas, of the particles will be 2px, which corresponds to a change of the momentum of the wall. So change of momentum is basically 2px, where px is the x component of p if this axis is x. So have you seen this type of calculation already? Maybe yes, maybe not. No answer. Anyway, the change of momentum, now remember that F is equal to dp dt, therefore a change of momentum is proportional to the force, so the 2px must be basically force times dt. temporal interval. Okay, and now if you divide by the surface, suppose that the surface has a length 1 meter squared, for instance, if you are at 1 meter square, basically this equation is telling you, if you divide by a surface, that the 2px is actually proportional to a pressure, but the pressure due to a single particle, okay? I'm doing this calculation in a very empirical way because, well, I'm pretty sure that you have done it before. So basically the idea is the following. You have a wall, you have a particle going and having a collision with the wall and coming back with the same momentum, just opposite direction. The change of the momentum of the particles must be equal to the force acting between the particles and the wall times temporal interval, right? Because dp dt is equal to f. Once you have the force, you derive by the surface, and then you get the pressure. Therefore, the pressure, the contribution to the pressure of the gas as due to a single collision between a particle and the wall, it must be proportional to the 2px, okay? Now, of course, we have to integrate over these particles of the distribution of particles to get a final formula for the pressure, which is the following. So P, where P is pressure, is equal to the integral. Now I will write it first and then I will comment. Vx larger than 0, so positive velocities, because I'm selecting the particles having a Vx component positive, if this is the axis X, and I'm considering just the right-hand wall, the pressure of all the other walls will be the same. Now I have to integrate over momentum, so I do dp, and then I have to put 2px, which is the variation of momentum of the particles, which is proportional to the force acting on the particles. Then I have a Vx times F0p. Now, what is this number here? This is the flux of particles. Okay? This is a flux of particles. Flux means number of particles, per unit, well, per surface and time. Okay. Indeed, let's try to do a sort of dimensional analysis. So let's say that dn is equal to volume times F0p dp, from which we get that F0 dp must be as a dimension 1 over volume. Okay, so let's try to see if it works. So dp F0 as a dimension 1 over length cubed. Then I have a Vx, which is length divided by time. Then I have a Px, which is mass, length divided by time again. Okay. Which means that I have, let me see if everything is correct. So the velocity is length divided by time. Then I have 1 dp, and f0 must be 1 over this, and then I have ml. Okay, yeah, that's correct, I think. And that means that the dimension of what we have on the right-hand side is mass divided by length and t squared. Okay, so this is the dimension of what we have on the right-hand side. Which is the dimension of a pressure? Well, the pressure, what is the pressure? Is a force divided by surface. And the force, what is a mass times length divided by time squared. Then I have 1 divided by length squared, which, because it's a surface, which is m divided by t squared L, which is exactly what we had there. Okay. So dimensions are correct. So it is indeed a pressure, having a dimension of mass be divided by length and divided by time squared. And well, the reason for which this is correct is clear, and the interpretation is that basically this is the flux of particles, so the number of particles per unit time in unit of surface, and this is basically the momentum exchange, which is the force which a single particle is exerting on the surface as due to the collision. Okay. Now let me change page. So we said that P is equal to the integral over the Vx larger than 0 dP 2px Vx f0 of P, which can be written also as dP, and I will comment in a moment on that, PVx f0 of P. Basically, what I'm saying here is that since we do not expect any asymmetry between the positive and the negative sides of the x-axis, in doing the integral over 2 Vx for positive Vx is equal to integrating over all the possible direction of, well, all the possible sign of Vx, so positive and negative with the same number, okay? So this is by symmetry. And so this can be also written as the integral over dP of px squared divided by m. And then let me put, instead of f0, c e to the minus p squared a. Okay, because p0 was this function here. Now, another thing that we can do is the following. This can be interpreted as a sort of average of px squared. It is the average of px squared, because basically I'm taking px squared and I'm multiplying this by a distribution function, and then I'm integrating over. Now, there is no reason to expect that the average value of Px is different from the average value of Py and the average value of Pz, okay? So, again, by symmetry, let's say that if we average Px squared, this must be equal to the average of Py squared and the average of Pz squared. Therefore, instead of writing px squared, now we can write dp p squared divided by m, but adding 1/3. Okay? Where p squared is just px squared plus py squared plus pz squared. So by symmetry, since this term here can be interpreted as a sort of average over p of the variable px squared without Gaussian distribution, I expect the components px, py, and pz to have the same averages, and therefore the average of px squared is just 1/3 of the average of p squared, of the total moment. Okay. Okay, so this also, let me put a 2 here and a 2 here, is 2/3 c times the integral over dp of p squared divided by 2m e to the minus p squared a. And this is the pressure. This is the pressure. So let me see how is better to proceed. Maybe the best way is the following. So the pressure is 2/3 c integral dp p squared a p squared. Now this is microphysics. Or microphysical, because it's something derived from kinetic theory by expressing the pressure as a sum of contribution of the single interaction of a particle with the wall. And this is also equal to, from ideal gas law, because we started the Boltzmann equation by saying that it is a dilute gas. And also we know that for a dilute gas in thermodynamical equilibrium, we can use the equation of state of ideal gas. And this is equal to Kb and T. Okay? Remember that PV is equal to Kb and T. Okay? So this allows us to determine the constant A, because now it's a matter of doing the integral. Well, actually, we know the value of c. So we have that 2/3 c. C was n, and we had a divided by pi to the power of 3/2 in the 2/3 c, which is n a pi 3/2, integral over dp of p squared to m e to the minus p squared a must be equal to kb and t, from which I can remove the n. And now it's a matter of computing this integral. Just telling you the result. The integral from 0 to plus infinity of dp p to the power of 4 e to the minus p squared a is equal to, you can do it by using Mathematica, for instance. And I have a to the power of 5/2. Mathematica. Let me change page, and I will stop in a moment for a break. So let's see, what do we have? I have a 2/3, then I have n, and I have a to the power of 3/2 divided by pi to the power of 3/2. Then I have a 4 pi coming from the integral.
Scusi.
Sì, non ho cambiato pagina, hai ragione. Ok, so 2/3 n e to the power of 3/2 pi to the power of 3/2. Then I have a 4 pi coming from the integral over the solid angle. Then I add a 2m at the denominator. Then I have this 3/8 square root of pi and a to the power of 5/2. This must be equal to n kbt. So we need to do some simplification. And at the end, so the pi basically pi and pi. The pi cancels, this and this, 2, 4 with the 8, 3 and 3, blah, blah, blah. And at the end, you get the A is equal to 1 over 2 mkbt. So at the end of the day, the F0 of P is equal to a density, particle density, divided by 2 mkbt pi to mkbt pi to the power of 3 alpha, because this was was equal to n times a divided by pi divided by 3 alpha. And then at the numerator, I have e to the minus p squared divided by 2 mkbt. Now, this is exactly the Maxwell-Boltzmann distribution that we will derive in a different way later. Okay, which is basically the solution of the Boltzmann equation in stationary condition. And under the hypothesis of uniform system. Okay. So what we get is that if we solve the Boltzmann equation in stationary conditions, so that means once we have reached the thermodynamical equilibrium, the distribution function we are talking about, this F0, is just the Maxwell-Boltzmann distribution. Okay. Have you seen this distribution already, the Maxwell-Boltzmann?
Yes, we did.
Okay. Just let me make a check on the dimension. And now we will write it in a slightly different way. Let me see if dimensions are correct. We said that F0 of P dP must have dimension of 1 over volume. Okay. Okay. This must be the dimension. And indeed, let me see here. Here I have n, which is 1 over volume. And at the denominator, I have a kbt times m. Now, which is the dimension of this? This should be dimension momentum squared, because kbt is an energy, which is a momentum squared divided by mass. Therefore, mkbt has a dimension of p squared. Mkbt is a dimension p squared, therefore this is a dimension p cube. And so then this is correct. Okay, so if I multiply by dp, then I get that F0 p dp is 1 over volume as a dimension. It's useful to do dimensional check, usually, okay? Indeed, and then I promise that I will stop for a break. Well, F0 p dp is equal to n divided by 2 mkbt pi to the power of 3 half e to the minus p squared divided by 2 mkbt. Then I have dp, which is 4 pi p squared dp. This is basically telling us the way to compute the number of particles, number of particles per unit volume, with momentum having a size between p and p plus dp. Okay, so this is the interpretation. So this, if you want, is the probability of having modulus of momentum p. Okay. And another way to write the Maxwell-Boltzmann distribution is to express directly the velocities in the following fashion. So let's see what we can do. So dpf0p divided by n, now this is equal to 4 pi p squared, 4 pi p squared dp. Non ho cambiato la pagina, grazie. dpf0p divided by n is equal to 4 pi p squared dp e to the minus, let me put here instead of p squared. So before we have the p squared divided by 2 mkbt, but this is just 1/2 mv squared beta, where beta is 1 divided by kbt. I'm writing this in terms of velocity. It's just this trivial calculation, okay? And I think I forgot something. Yes, the denominator, which was 2 pi m kbt to the power of 3/2. And of course, this can be also written by introducing dunque 4 pi d pi, la n l'abbiamo messa lì, ok, this is also equal to 4 pi m squared v squared. Now p is equal to mv, therefore dp is equal to m dv. And so here I am another m, another dv, e to the minus 1/2 mv squared beta, where v squared is the modulus of the velocity. And let me see at the denominator, we had, we have again the same structure, so 2n kbt to the power of 3/2. Okay. So then at the end of the day, we get something like that. So we have a v squared e to the minus 1/2 mv squared beta. Then I have a dv, and at the denominator, we have a kbt to the power of 3/2. And let me see what we have there. We have m to the power of minus 3/2 and a pi divided by 2. Because we had 3/2 minus 1, which is 1/2, and then I guess that this is also square root of 2 must be correct. So let me check if the calculations are correct. Okay, so this is the Maxwell-Boltzmann distribution in velocities. Boltzmann. Okay, so this distribution basically is telling us that you have, well, if you try to make a plot of this, you have a v squared times an exponential. So, well, 0 must start from 0. Then you have a maximum, and then you have an exponential cut at infinite velocities. Okay. So basically, as I said before, the stationary solution of the Boltzmann equation, at least in the case of f equals 0 in uniform system, provides us the distribution of velocity at the thermodynamical equilibrium, which is exactly the Maxwell distribution function for velocities. Okay. And we will do at least a couple of exercises on the Maxwell distribution of velocities because it's interesting. But now I stop for a few minutes, and then we will formulate and then maybe also show the H theorem. Ok? So facciamo una pausa. Ok. Possiamo cominciare? Ci siamo?
Io ho una domanda da farle.
Sì.
Ad un certo punto abbiamo detto che potevamo usare la legge dei gas ideali perché eravamo partiti in una condizione di gas rarefatto,
Mhm.
equilibrio termodinamico.
Mhm.
Siamo certi di essere in equilibrio termodinamico perché siamo partiti da F0?
Sì, perché siamo stazionari, ci stiamo mettendo sì, in una situazione di non dipendenza da T e quindi ci aspettiamo che quella sia la situazione di termodinamica all'equilibrio perché niente cambia più, no? È stazionario.
Ok, grazie.
Mhm. Prego. Okay, so in principle, the Boltzmann equation is telling us, well, the final state, as said before, so for time going to infinity, the F will try to approach the equilibrium distribution function, okay, which is the F0, which is the equilibrium distribution function. Corresponding to the thermodynamical equilibrium, but in general, F has a time dependence that can be computed only by solving the Boltzmann equation, at least in this scheme. Okay? There is something that we can do. We cannot solve this equation for even simple cases because it's very complicated. It can be solved numerically. We can just find the stationary solution, but what we can formulate and then actually prove the famous H theorem. The H theorem is telling us the following. Suppose that you define a quantity h of t, which by definition is the integral over dp of f of pt log of p and t, where I'm assuming that f does not depend on r, but it is the solution. It is the solution of the Boltzmann equation. Therefore, we are in presence of molecular chaos. Molecular chaos. Chaos, I think, is written with the H. So under this hypothesis, the H theorem basically tells us that the derivative of H with respect to T is less than zero, is less equal than zero. Okay, now comments. The formula that we have there, F log of F, there's something missing here, of course. F log of F, it's very similar to the Shannon entropy or Gibbs entropy, okay? Similar to Gibbs entropy. Indeed, in that case, we had now the case of k possible states and particles, and there we had the pi, the sum of pi log of pi. So here the structure is very similar. Instead of a sum, we have an integral over momentum, and instead of pi log of pi, we have f of pt log of f of pt. So the structure is very similar, and indeed, I will comment this at the end. This function here, the h of t, is basically proportional to the entropy, to the thermodynamical entropy in the limit in which we have the Maxwell distribution function instead of f. Okay, so at equilibrium, basically h corresponds exactly to the entropy. Okay. The theorem establishes that if you take the function, the distribution function coming from the solution of the Boltzmann equation, then you compute this quantity and you derive this quantity with respect to time, the derivative of this quantity is always negative, or at least equal to 0. Okay? Now here on that one can have a lot of discussion, because basically the H theorem was criticized by many physicists at the beginning, and at least that was one of the reasons for which Boltzmann made suicide at the end, because we started with microphysics, which is which has the time reversal symmetry, because we say that the matrix elements are symmetric with respect to the exchange of initial and final state, and we end up with a formula that is clearly violating time reversal, in the sense that the derivative of this quantity is always less than 0. Okay, which is somehow reminiscent of the second principle of thermodynamics, indeed, in which we say that for an isolated system, the entropy increases in time. Okay, so I will comment this later on, but let me just show analytically that this is actually the case. So suppose that we want to take the derivative of h with respect to t. Now, and considering the definition, this is the integral over dp of the derivative, partial derivative of f with respect to t times the log of f plus f divided by f derivative with respect to t of f. Okay, this cancels. So this is equal to the integral over dp. I can collect a partial derivative of f with respect to t, and then I get here 1 plus the log of f. Okay, now I know that df dt, sorry, f of pt is equal to df dt call, again for a uniform system, and f equal to 0, which is actually this almost the same, in the sense that we expect that if there are no external field, well, the system should be uniform. And so instead of the partial derivative of f with respect to p, we can substitute the collisional integral. Okay, so therefore this is equal to the integral over dp, and then I have the collisional integral, which was dp2 dp1 prime dp2 prime tif squared. Then I have a delta 4. Let me put delta 4 of conservation of energy and momentum. Then I had here of f1 prime, f2 prime minus f times f2. And here I have a 1 plus the log of f. Okay? This, let's call this equation 1. So where, as I said, instead of partial derivative of f with respect to time, I substituted the collisional integral. Notice that another integral appears here, which is dp, which was in the definition of h. Now let's take 1 and change p with p2. and P2 with P. Of course, nothing changes, no? Well, if I do that, basically I have the integral, so dH over dt is the integral over dP2, then I have the integral over dP. Let me just put one symbol for the integral, for simplicity, dP1 prime, dP2 prime, TIF squared, delta 4, and then I have here F1 prime, F2 prime minus F2, 1 plus the log. Here I have the log of F2. Okay, so I take expression 1 and just change P with P2 and P2 with P. The integrals are the same. The only difference is that I have here 1 plus log of F2. Okay? But if I exchange P and P2, since we are integrating over them, I do not expect any difference. So let me call the last equation, let me call this last equation 2. So 1 and 2, they are equal because exchanging exchanging P and P2 does not make any difference because the distribution is the same, is F of P, and I'm just exchanging particle, let's say, with momentum P and particle with momentum P2, but I'm integrating over all those particles or over all those momentum, therefore I will get the same results. So that means that dH dt can be computed as 1 plus... Sì, grazie. Scusatemi. So dH dt can be computed as 1 plus 2 divided by 2. And let's write it explicitly. dH dt is equal to 1/2 integral dP, dP2, dP1 prime, dP2 prime, TIF square modulus, delta 4 of conservation of energy momentum. Then I have here, I have F1 prime, F2 prime minus F2. And here I have 2 plus log of F2. Okay? I'm just summing 1 and 2 and dividing by 2 because they are the same. And let's call this equation 3. Now take 3. And you can do the following exchange again. Instead of P1 prime, let's put P, or vice versa. And instead of P2 prime, let's put P2. And of course, nothing changed in the matrix element because TIF squared again is TFI squared for time reversal. Therefore, I can write that dH in a similar way. I can write the dH dt by doing this exchange is the equation 3 with this exchange. So it's 1/2 integral of, here is the same, dP2, dP1 prime, dP2 prime. The matrix element is the same, the delta 4 is the same, and here I have a difference instead because here we'll have F2 minus F1 prime, F2 prime. And here I have a 2 plus the log of F1 prime, F2 prime. Since I'm exchanging P with P1 prime and P2 with P2 prime. Okay. Let me check this equation, sorry. ff2, f1 prime, f2 prime, 2 plus log of f1 prime. Yeah, okay, let's call it 4. Now, again, 3 and 4 are the same because it's just an exchange of name of momentum from initial to final, but we have time reversal. From the initial to final, we need to have the same result. Therefore, I can finally write that dH dt is equal to 1/2 3 plus 4, which means 1/4 integral over dp, dp2, dp1 prime, dp2 prime, TIF square modulus, delta 4 of conservation of energy. Then I have 3 plus 4 there, which means that if I do the calculation, consider that here I have, with respect to this term, I have a minus. Then I can collect f2 prime, f1 prime minus f2, f2 prime, ff2. Then the 2 drops, and I have a log of ff2 minus the log of f1 prime, f2 prime. Okay. Now, let's look at the sign of what we have here. These are integration. This is square modulus of a matrix element at delta 4. So nothing basically have a sign that can change there, but for this, and let's write it explicitly, f2 prime, f1 prime minus ff2 times the log of ff2 divided by f1 prime, f2 prime. Okay. Now this quantity is always less or equal to 0 because let's call it, I don't know, A and B. So this A minus B times the log of B divided by A. So if A is larger than B, I get a minus sign from the log. If A is smaller than B, the log is positive, but is negative. A minus B is negative. So this is always less than 0. And therefore, that means that derivative of H with respect to T must be always less than 0. Okay? So it works. The H theorem works in the sense that this quantity that is defined by Boltzmann, this H quantity, which is very similar to the Shannon entropy, or Gibbs or Shannon entropy, is actually evolving always with a minus. So it's decreasing in time. And moreover, what happens, so dH dt is always less than 0. And actually, when dH dt is equal to 0, that means for what we have derived before, that means that f2 prime, f1 prime minus ff2 is equal to 0.
Prof.
Ah, non ho cambiato il foglio. Scusatemi, veramente non ce la faccio a fare lezione sulla tavoletta grafica. dH dt less than 0 and dH dt equal to 0 implies that f2 prime, f1 prime is equal to ff2, which was exactly the condition for obtaining equilibrium or stationary or the stationary solution of the Boltzmann equation, and therefore this happens when F actually coincides with the F0 that we derived before. So F of PT is going to F0 of P One is non-equilibrium, the other one is equilibrium, thermodynamical equilibrium, and the derivative of H with respect to time is always negative. Okay, so we have a direction of time which is provided by the sign of H. Okay, so to some extent, this is a microscopic description of the second principle of thermodynamics. The second principle of thermodynamics is stated in terms of entropy, which is a quantity which is defined only at the thermodynamical equilibrium. So you start from a thermodynamical equilibrium condition, then you make the system evolve, and you cannot say nothing in thermodynamics about the evolution of a system. When the system reaches again a thermodynamical equilibrium condition, you know that the entropy increases for the isolated system. The Boltzmann equation goes beyond that because it allows to describe how equilibrium is reached as a function of time. And we have initially, let's say, a distribution function which depends on P and T, which has general form. We know that as the time evolves, at the end, we will need to recover an equilibrium, which is obtained when the derivative of H with respect to T is equal to 0, so when H is stationary, and we get exactly the Maxwell-Boltzmann distribution, okay? So it's a very powerful tool in order to describe system out of equilibrium and how those systems approaches equilibrium, okay? And the quantity that we have there, H, is very similar to the Gibbs entropy, and actually, if you try to do the following, so H is equal to dp f of pt log of f of pt, one can show, I will not do it this, one can show that if instead of P I put F0, so exactly the Boltzmann distribution, the Maxwell-Boltzmann distribution, then H is proportional to minus the entropy. Okay, so this quantity, apart from the sign, is just the entropy at the thermodynamical equilibrium, apart from some proportionality constant. Okay, you can try to do it. Basically, one has to substitute the F0, and then basically one can show that this is proportional to the entropy. So actually is proportional to U divided by T, so internal energy divided by T, whose variation is the variation of entropy. Okay, but I will not do this calculation. Okay. So which is the message of all of these? Is that the message is that we can have a sort of law of increase of H, so here decrease of H, which corresponds, which is a sort of microscopic description of the second principle of thermodynamics. Okay, if a system is out of equilibrium, it has a distribution function f, which is different from the Maxwell-Boltzmann distribution. The system will naturally evolve towards the thermodynamical equilibrium, at which point the distribution function is the Maxwell-Boltzmann distribution. Okay, that's the message. Just a comment on, let's say, conceptual issue that was raised against the H theorem of Boltzmann. The thing is that we had derived this result by using time reversal symmetry, in the sense that we say that the matrix element is invariant with respect to variation to the inversion of time. And at the end, we obtained a result which is actually violating time reversal, because we have a quantity h which is related to the microphysics, whose derivative is always negative. How is this possible? Well, the thing is that F is a solution of the Boltzmann equation, and F was derived under the assumption of molecular chaos. Okay, so basically one can show that the violation of time symmetry is due to the simplifying assumption of molecular chaos. Because when adopting the molecular chaos hypothesis, one neglects the correlation between momenta. Therefore, if you try to invert time, and look at the system before and after the collision, if you are neglecting the correlation between the momenta, what you get after the collision or before the collision is completely independent from each other. So the possible correlation, so if you have two momenta, the two final momenta are correlated, but if you assume, for a scattering process, but if you assume that molecular chaos holds true, they are uncorrelated, and therefore you cannot reconstruct, let's say, the initial state from the final state by just inverting time, because you are losing information. So molecular chaos basically is telling you that the system is evolving in such a way that you are losing information, and the loss of information is a clear violation of time reversal. Okay, so the issue is very complicated also in the conceptual point of view, and I also can suggest you some books to read on this issue, but it's still very fascinating, because at the end of the day, the reason for which the second principle of thermodynamics holds true, well, it's a statistical principle, so it's not valid, strictly speaking, at the microscopic level. Nevertheless, it's still somehow puzzling us. It's still puzzling us. It has to do, if you read the book of Wang, for instance, or Landau, it could be that there is some source of time reversal in the microphysics. For instance, think about big interactions, but maybe there is something more. Well, maybe this is not enough actually to explain the violation of time reversal in macroscopic systems. Okay, maybe the universe was created in a situation which was very particular from the point of view of entropy, initial entropy. And with this I stop, because it's 11, and I guess that Luciano maybe is already there. So see you next Tuesday.
Thank you, bye bye.
Arrivederci. Ciao.
Arrivederci. Buona giornata.
Arrivederci.
Ciao.